What if I tell you that the sound of a healthy plant is mimicking a Beethoven sonata? What if I tell you that the sound of this plant is mimicking the sound of a healthy heartbeat? This plant is one of the plants of our Tsinghua campus, and it's reflecting the species that are next to the plant itself, the water fluctuation. Together, these two elements define plant fitness, or more broadly, what we call ecosystem fitness, which is not just a biological signal, but it's a byproduct of the plant interconnection within the larger ecosystem it belongs. Since I was a child, I fell in love with nature, colors, textures, shapes, water, and all the interconnected elements of ecosystem. This one is a salt marsh in my hometown, Venice, that is highly biodiverse and highly functional, such as it provides services like flood risk reduction and carbon sequestration. The study of nature, the discovery of nature, was what I made my career. And in particular, I studied the collective behavior of species, that how different individuals of the same or different species react to an environment, how their dynamics is providing a function, not just for the species itself, but also for people. I also experienced natural disasters that are related to ecological change. My house was flooded in 2010. I experienced landslides, spread of infectious diseases, spread of invasive species, and heat waves. All these phenomena are related to alteration of nature, alteration to ecological network. I studied structural engineering and hydrodynamics, which gave me the tools to tackle this problem, how to put things together as a structure, and how this structure or elements of the structure propagates, for example, through water networks. In my group, we are advancing the science of ecosystem engineering that on one side is measuring at very high resolution the risk of ecological alteration. Recently, we estimated that 78% of the worldwide population lives under high water stress. It can be flood and drought that compounds over space and over time. And China, for example, unfortunately, is the country with the largest share in terms of economic exposure. We have $1.25 billion a year of damage in relation to these water extremes. Most of the water extremes are experienced by the largest river delta worldwide. For example, the Pearl River Delta, the Ganges River Delta, and the Mississippi River Delta, that are areas that host a large portion of the human population. So the question is, how do we solve this problem, but also how do we produce the services by harnessing the power of nature? How do we engineer nature? We do that through an initiative that I'm announcing today, a planetary initiative called EcoWeave, that looks into the structure of eco-hydrological opportunities as network, a proactive, participatory, and perspective initiative where we partner with the public sector and public sector, where we bond nature in the way it's supposed to be. So this initiative is supposed to collect a variety of different ecological restoration projects worldwide and make them global, make them interconnected. And on one side, we need to consider the risk that we face, that are collective risks. Because, for example, if we restore the Amazon rainforest, that has a consequence for the global climate. And maybe it is impacting the floods that we have in Shenzhen. Or vice versa, the restoration of Shenzhen mangrove have an impact in South America. So this initiative is really trying to make a global, local reconnection of nature by acting in water and by acting on the key species that bond nature together. Methodologically, how do we approach the problem? We use network science, and particularly one of the models that I developed in the past as the core foundation of this eco-engineering approach. This model is able to infer these large-scale dependencies, accounting for black swan phenomena, butterfly effects, and also nonlinear waves that can be related to water or species variability, to define an eco-hydrological safe zone in between minimum and maximum extreme, but also accounting for the baseline flow that are needed, for example, for the production of products and services with the human value. We use water for producing things. We use natural resources to produce things. So we must account for those demands that are also putting a pressure into our ecosystem. If you take any ecological map, for example, the IUCN habitat map, the information that you get is very limited. You have this sequence or set of habitats without any interconnection. So we don't know the dependencies of this habitat. We don't know how many species we have on this habitat. So in my group, we are improving the maps by including ecological complexity, where species are, as well as hydrological complexity, the water dependency that links the habitat together. Just to give you an idea, we develop a functional connectivity index that defines the extent of river fragmentation as well as the flows. And if you put that into the current habitat map, we are able to assess how much this hydrological network have an influence into certain ecosystem functions, such as total surface water retention, that currently is at 65%, biodiversity, 55%, conserved if you consider the current fluxes and connectivity, and 60% of the total carbon stock into the habitat. If we restore the connectivity just geometrically, those performance indicators are bumped up by 30%, which means that you can protect 95% of the total surface water available, 85% of the total biodiversity, mostly vegetation, and 90% of the total carbon stock in any habitat worldwide. That must account for basin boundaries. Basin boundaries are determining where water flows. Each basin is like an independent organism where the bloods act as a vessel, and for example, the carbon are like the metabolic fluxes related to the evapotranspiration of that particular basin. And basins are actually also formed in the ocean. We have ocean basin with its own biodiversity, with its own carbon fluxes. So nature has boundaries, and we must account for those boundaries in the way we formulate our restoration potential. One of the applications that we did here in South China was about the South China tiger. And we evaluated the potential for restoring or recreating the novel ecological corridor with the potential to reintroduce this species as an iconic rare species as a good excuse to enhance the ecosystem function in this part of the world, which is also a multi-habitat approach that accounts for croplands, for urban ecosystem that can be regreened, revegetated, biodiversity can be revitalized, which has consequences, for example, for hydrological regulation and carbon sequestration enhancement. And we are doing that thinking about the future, because the future is not as happy as we may think. In particular, considering extreme wetness index or phenomena and extreme dryness index, we are tracing the teleconnection that are networks with the large-scale dependencies or temporal dependencies that establish how much the habitat restoration in a particular place has a positive or negative impact into the climate. It's not just about measuring climate impact into ecosystem, but measuring how habitat restoration affects the climate. It's a bidirectional feedback, which is really, really important also for the policy making, for creating policies that rank priorities for restoration worldwide. And in this web of nature, I think a very important role is played out by the design, the development of novel urban ecosystem. that should be more green, more interconnected, precisely like nature. We cannot just build a building one after another in isolation and reconnect them a posteriori, because that just doesn't work. For example, if we do that, first of all, we can enhance biodiversity from the microbial scale all the way up to large scale. This one is acting on the structure of vegetation. And the structure of vegetation has an impact into how much water flows back into the atmosphere. That's called evapotranspiration capacity. So given any climate zone, the way in which we should redesign urban ecosystem is to restructure both the vegetation and the built environment in a way that is mimicking nature, that is ingrained into the landscape of nature. At the micro scale, what I was able to do in my lab is also to fabricate networks from the fine balance of clay, an ecological binder, and water. This relative proportion of material and species is actually leading to the self-emergence of nature under an environmental stress. So nature itself is responding to stress by connection, because connection distributes the stress over space. And that network has a temporal impact. For example, this structure, they soak up water from the atmosphere and even carbon, and they release it when you have a temperature gradient. So they are creatures that are alive. And they can be applied into indoor environment for controlling the microclimate, as well as to larger scale system, for example, coastal system, for enhancing the restoration capacity. Because if you fine-tune the little ingredients, once again, for example, clay, vegetation, and water, you really have the self-emergence of this network, which brings certain services, such as carbon capacity enhancement, as higher to the level that they can sustain. So we are working not just on terrestrial system, but the coastal and marine system, and we are thinking about how to trigger this particular self-emergence in a way that accounts for this functional connectivity. Functional connectivity that increase the soil organic carbon when you increase the area. So networks define form, and form defines function. Based on that knowledge, we are predicting the impact, the beneficial impact of this blue carbon ecosystem restoration against expected riverine and oceanic floods at very high resolution, 30-meter resolution, locally and globally. Because we wish to provide evidence, quantitative evidence, as detailed as possible about the benefits of our ecological restoration, because we wanted to find partners that can finance that restoration. Beyond that, we are providing baseline information about the total surface water that the vegetation and other species can support in this ecosystem. It's not just about extreme value, but it's also water capacity. How much ecology provide water to people? It's not just about vegetation, it's also about keystone species that support the vegetation in its own function. If you take a mangrove forest, you can monitor the fish, because the fish contribute through the biological food chain to the function of the mangrove. If you collect videos and you monitor the fish behavior, you can reconstruct a functional network where the randomness of this functional network corresponds to the malfunction of the system. The more organized the network, the better the system is functioning. And there is a duality between network structure and function, for example, of the mangrove in this case. The more organized the network of the fish, the more organized is the mangrove network, and the higher the carbon sequestration capacity. With that knowledge, together with some students, we created this spin-off initiative of the university that is called C2C. We are able to inform where and when it's safe to do the fishing. The variability of the fishing, again, affects the whole ecosystem function. So it is really important to provide to the relevant stakeholders the information that is necessary for their own activity, for the decision making, at whatever scale you want. And the local scale of this fish was sponsoring the coastal restoration. This one is the sound of a very healthy mangrove just next to the beach where my son is standing. I believe when I see this picture that the future of ecosystem should be to provide ecosystems that are like this or even more beautiful. We have the capacity to increase the beauty and the function and the melody produced by ecosystem through a set of our eco-informed decisions. Informed decision that must be coming from the science as well as from what people can do. So connecting with the key stakeholders is really crucial for the survivability of future Earth. That's why, if I go back to my original plant that was sounding like a Beethoven, that plant is also sounding in that way by design. Somebody designed our campus in a way that it's functional. And in the same way, we must connect with the people, like the one that formed me. My colleagues, my friends, my students, my family, they nurtured me, they made who I am, and I connected with them to be a man that is able to grow, that is able to function efficiently. We must do the same for planet Earth, because our synchrony is our symphony. And I think that's a sign of collective love for our environment and for our people, all the people of the planet. Thank you.